Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Today, let's talk about nature of light. So when we talk about light, the light has a wave nature first. So when you see a beam of light or see a white light in nature every day, white light is not just a one, pure substance. It's actually a mixture of different lights together. And light can also be called the electromagnetic radiation, a fancy name of the light. If you want to know why it's called that, because light is a transfer of electricity and magnetic field moving forward. So light can also be called electromagnetic radiation. And also the light has a wave nature. Wave nature means it moves forward like a wave. And for wave, it can be splitted or diffracted. When you see a rainbow in nature, you see there are many, we call it 7 colors of the rainbow. It shows the split of the nature light. And that split is because nature light is made of, as I said, a mixture of different light waves. When we talk about waves, I'll give you a few examples, and there are some properties you need to know about a wave. First is a wavelength. It's the distance per cycle. As you can see, these waves move forward along the a-axis in a cycle, up and down, up and down, up and down. Okay, so the distance between the two neighboring highest peak, the distance between these two is called wavelength. How long a wave is, if you can imagine that way. Okay, so different wave will have different wavelengths. You see this red wave has longer wavelengths, the blue one has smaller wavelengths, and the yellow one has smaller wavelengths, and blue one has the smallest wavelengths, right? So another concept besides wave is a frequency. Frequency is equals to cycles per second. So if you know the frequency of engine, maybe not an engine, a fan, each second, how many circles does the fan rotate? That's called a frequency. So in the light, the frequency means the cycle per second. In each second, how many wavelengths it can complete, it can move forward. That's called a frequency. And we use the Greek letter nu to present frequency. And for wavelengths, we use Greek letter lambda to present frequency. Besides the frequency and the wavelengths, there's another two, actually. One is the period. Period is how long does the wave takes to move forward for a length of wavelengths. Okay, so if at 0 point, the blue wave is at this peak position. After 2 seconds, it moved forward. Okay, after 2 seconds, the wave moved forward and you are moving on to the next peak is moved forward to this 0 position. And then the period of this wave is 2 seconds. So the frequency and the wavelengths, if you time frequency and wavelengths together, then you will get 1. Okay. Finally is amplitude. Amplitude is how far away the peak of a wave is away from the central of the wave. So as you can see here, there are 2 waves. One is very tall in the top peak and very tall in the bottom peak, negative peak, or we call that. And the other wave has a lower higher peak and lower wave peak, lower negative peak. So for compare these 2 waves, the taller peak has a higher amplitude, okay? And the lower or darker red wave has a lower amplitude. Okay, so amplitude is another thing you need to know. For light, in the vacuum, the light travels at the same speed. So on Earth, in air, we assume approximately think they travel around the same speed. So for all the questions you come across in this lecture, in this class, you can treat the light of speed is 3.00 times 10 to the 8th meters per second. Okay, so this is a constant. And for all light, the speed of light equals to the frequency times the wavelength. Frequency should be in the unit of hertz or per second. So per second is derived SI unit that equals to 1 hertz. The unit of wavelength should be in the standard basic SI unit in the meter. So if you use hertz and meter, then the speed of light is in the meter per second. Okay, so all these SI units should be in the same system. In other words, if you use 7 basic SI unit or the derived SI unit, which is made up by the 7 basic SI unit, does not matter how you do, what equation you use, the answer you get from this equation should also be in the 7 basic SI unit or the derived SI unit. Like here, unit of frequency is per second, unit of lambda is in meter, then naturally what you get, the value of unit of speed of light should be in meter per second. All right, so since there are different wavelengths of this light, and then the light can be, as you can see, the rainbow, there are different colors, and obviously there are different, different types of lights. And we can make a spectrum that collects all wavelengths of light and put them together in a diagram. So you will see it here, the electromagnetic spectrum, the spectrum of light. On top, you can see is a wavelength with the increasing of wavelengths. In the bottom axle, it's the decrease from right to left is decreasing of frequency. So you can see from this too, the smaller the wavelengths, the higher the frequency, which makes sense, right? Because C equals to nu times lambda. If the speed of light is constant, the bigger the wavelength, the smaller the frequency. Okay, so with this, there are so many different wavelengths, so many different type of lights. If we, starting from the lowest wavelength or highest frequency is a gamma ray. And then larger than that is X-ray. After X-ray is ultraviolet. After ultraviolet light is visible light. Okay, and then infrared, microwave, and the radio waves. For human, only visible light are visible to us. So we can see the purple from blue, from green, from yellow, orange to red. So in terms of wavelengths, we can only see light with the wavelengths from 400 nanometers to 750 nanometers. Okay. So it's really a small, narrow region of light from all the electromagnetic spectrum. Okay, so when we talk about these lights, we mentioned that light has the features of wave. They behave like a wave, but also light has some property of particles. Let's talk about that. The black body radiation. Well, sounds very physics, right? It actually means light is emitted from a hot object. Hot object, if it's not hot, it's black, right? It does not emit light, then we can say it's black. It's called a black body. Okay, so one most common example of the black body radiation is a light you will see, the light bulb you see. When you make current going through this filament, then this filament will start to warm up at some point. Well, it happens there quickly, of course, but it will start to emit light. Okay, and that black body radiation, we can use the idea of energy to explain that. Okay, so if you have a hot object, hot means you have very large amount of thermal energy. if the object is getting hotter and hotter, you have more and more thermal energy. At some point, this object cannot hold this thermal energy anymore, or this thermal energy wants to convert into another type of energy to make the whole system more stable. In this way, the black body radiation, the extra thermal energy is converted into the energy of the light. So, and light does hold some amount of energy. The energy of light, in this case, E, equals to n times Planck constant times the nu, the frequency of the light. Okay, this nu is called quantum number. It's actually just a positive integer. It means, 1, 2, 3, 4, 5, 6, 7, 8, you name it. Okay, so, and the nu is the frequency of light. So this equation directly links the energy of the light with the frequency of light. The more quantum number, the stronger the light is, but the radiation, the wave is the same, and the more energy you have, right? Okay, so this black body radiation shows the particle nature of light. Why we say the particle nature? Because of this quantum number. It's increasing. The energy of a beam of light can only increase by the minimum amount of h nu. There's another experiment that also shows the light has a particle nature. That's the photon electric effect. This is an experiment designed, and the effect was found by Einstein. Okay, so what it means is the photon electric effect is photon in, electron out. So let me explain that to you. We have this device. There is a glass tube, and it's actually pumped into vacuum inside. So nothing is inside, and it's sealed from the bottom plug. In this glass container, we have two posts, or two metal posts. One is just a metal, okay? It's a column shape. The other is a large sheet of metal. They call it evacuated tube. They call it a metal plate here. So outside of the sealed glass container, these two metal pieces are connected through a battery and through a current meter. Okay, so that means for now, if there's nothing in between, nothing changes in between of the metal post and the metal plate, you should not read any current here. And if there's anything showing up here and on top, if there's any electricity pass through this, you will see that change in the current meter. So what the experiment goes is you can use different types of light shining on this metal plate. The light can penetrate this glass tube, so that's fine. So light can actually go through this glass tube and hit on this metal plate. And interestingly, not all light can trigger this electron to come out. Only a certain light that goes above a threshold frequency can trigger this emission of electrons. So the photon effect is photon in, electron out, the light in, electron out, but it shows a threshold frequency of the light. And also there is no time lag, which means as long as you shoot light on, you can see the electron. For those who cannot trigger electrons, does not matter how long you shoot light on this metal plate, no electrons out. So there's no time lag. The response is instant. So based on these effects, Einstein developed the photon theory. What's it about is the light is made of small, tiny bundles of energies called photons. Okay, so when we talk about the substance, the smallest unit in chemistry, we call them molecules, right? Compounds, elements, atoms. So in the light, we call that smallest bundle of photon. Okay, there are different types of, there are photons with different energies. Okay, so each light has its own own photons of energy. And each atom generates one photon. Imagine how many atoms in this metal. So there are many photons are generated. Okay, so yeah, and each atom can generate or absorbs a photon actually. Yeah, so the energy of photon for one atom equals to h times nu. That means the Planck constant times the frequency of the light. And because each atom generates one photon, the quantum number of h nu is 1. Okay, and that should equals to the energy difference of the atom. So this is the photon theory. Basically, after understanding how this process occurs, this equation, energy of photon equals to h nu equals to delta energy of atom, is important, and you should know that. Okay, so let's take a look at energy problem. When we do this numerical calculations, we need to pay attention to two different equations for lights. Okay, one is C equals to nu times lambda. The other is energy of the light equals to n times h times nu. So these two equations are discussed in this video. Let's take a look at question. Calculate the energy of one photon of A, ultraviolet light, give you the wavelength that equals to 1 times 10 to the negative 8 meters, and B, visible light, with a wavelength that equals to 5 times 10 to the negative 7 meter, and C, infrared light, with a wavelength of 1 times 10 to the negative 4 meter. What do the answers indicate about the relationship between light's wavelength and energy? I suggest you to pause the video and take out sheets, scratch sheets to try to work out this question by yourself first. All right, so ABC is the same type of question. It gives you the wavelength and asks you the energy of the photon, right? And it's only one photon, so the n here equals to 1, right? So if we want to use the wavelength and to calculate photon, we need to use the bridge of this nu, the frequency, right? So we can transform or combine these two equations together. E equals to h nu, nu equals to c over lambda. So plug in that part in, E equals to hc over lambda. This is a very important equation, so hopefully you can remember it by heart. And then if you want to use the Planck constant as the 6 times 6 to 6 in the times 10 to the negative 34th joule per second, then you have to use a lambda with the unit in meter and the speed of light in the unit of meter per second, and then the energy in joules. So, okay, so for UV, we do hc over lambda UV. All the lights share the same speed, okay, speed of light, 3 times 10 to the 8th. Okay, plug in the numbers. We get the energy of one photon, one UV photon is 1.99 times 10 to the negative 17th joule. The same thing, plug in number for visible light. The energy is slightly smaller. So it's negative 17, now it's negative 19. 3.98 times 10 to the negative 19 joules for this visible light. And then the IR light, plug in the numbers, we get the energy of one photon of an IR light is 1.99 times 10 to the negative 21st joule. So we got the energy of all three photons, and we need to know the relationship between lights, the wavelength, and energy. Okay, so the wavelength from ultralight to visible to infrared is increasing. It's from negative 8th to negative 7th to negative 4th, right? The wavelength is increasing, but the energy is decreasing. Okay, so it's changing from negative 17 to negative 19 to negative 21. And again, we're comparing one photons. Okay, so if you have a very weak, if you have only one photon of UV light, but you have thousands photons of IR, then the energy may be different. But if you're comparing apple to apple, one photon to one photon, we can establish this relationship that the smaller the wavelength, the bigger the energy of one photon. All right, this is the end of this video, and I'll see you next time.